Solve this problem called count non-decreasing subarray after k operation. So in this problem, you are given an array nums of n integers and an integer k. For each subarray nums, you can apply up to k operation on it. In each operation, you increment any element of the subarray by 1. Note that each subarray is considered independently, meaning changes made to one subarray do not persist to another. Return the number of subarrays that you can make non-decreasing after performing at most k operations. An array is said to be non-decreasing if each element is greater than or equal to its previous elements, if it exists. So let's take a look at the first example. The input nums is this array, and k is 7, and the answer is 17. The explanation is that there are 21 possible subarrays in nums. You can quickly calculate that by using n times n plus 1 divided by 2 formula, where n is the size of the nums in here. And anyway, so after knowing the total number of possible subarrays are 21, and it says that only 361 and 631 and 6312 and 63124 and this 631244 cannot be made non-decreasing after applying up to k equals 7 operation. So you can kind of tell why it wouldn't work. So for example, 631. The target is to make this 631 non-decreasing. But each time we can only increase the element. So what it means is that we can increase, well, that's only one way to do it. Basically, we can only make this this 3 to 6, and then this 1 to 6 as well, which is the lower step we need to do. And you can see the cost here is 3. Cost is 3 plus, and the difference 1, we need to make it to 6, so the difference is 5. So we need to perform 5 here. So 3 plus 5 will equal to 8. 8 is strictly greater than 7. That's why it won't work. And actually, you can say there might be any like numbers after this 631, but as long as you cannot make this subarray non-decreasing, no matter what elements appear on the right hand side, it still won't. So that's why you can see in this example, this 631 is the first that violate the non-decreasing rule, and the second one is this is same subarray with the prefix of 631, and the third one is still with this prefix of 631 as well, and so on and so forth. And that's why there are like 4 such subarrays. So all the other ones are valid. That's why the answer is 21 minus 4, which is 17. That's why we should just need to return the 17 here. Okay. Yeah, that's pretty much like the gist of the problem description. And let's see how can we actually solve the problem. Okay, so to illustrate the idea of the solution, let's try to figure out this particular example. So the first thing that we need to do is to go from go from right to left in order to figure out the answer. So the motivation is that I want to know how many numbers that I can end with the current. So I'm going from right to left as nums I, for example, or as nums L as an example. Then how many R's on the right hand side, so I can match. So L, nums L all the way to R is valid. That's the main motivation. So once this is, if it is not valid, then R minus equal 1. And once it is valid, then we can answer plus equals to the length of this array, because you know, if the whole array, for example, this whole array is valid, and then surely this subarray will be valid as well, and 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 our way to just this element will be valid as well. So that's so we make sure once nums L dot R is valid, then nums L plus 1, then L R minus 1, nums L R minus 2 are all valid. So answer plus equal to the length of this subarray. So namely it's just R minus L plus 1. That's the main motivation. But how do we actually check if it is valid or not? That's where the next part comes in. We need to maintain non-increasing queue while going from right to left. The reason is that we are trying to keep the order that is non-decreasing, but we are going from right to left, basically the reverse order, so we need to keep a non-increasing queue. So here's what I mean. Okay. Let me see if I can copy this example to here. So, okay, we are going from right to left now. So first we go 4. So the queue is 4, and then we do nothing because everything is valid right now, and we visit another element, which is the next element. We do 4 again. It has nothing because it doesn't validate anything. So we visit the next element again, which is 2, and this is valid again, and we go all the way 1 and all the way to 3, which is we need to do something in 3. So what should we do here? Because this is 3, and before visiting this 3, the whole thing is non-decreasing. But here's the thing. What are we going to do about this thing, this subarray? Because if we just consider this subarray is not valid, so what is the cheapest way to make it valid? So because we can only increase, we cannot decrease. For some might say that why not just decrease this to 1? Yeah, of course it will make it valid, but as the problem description mentioned, we can only increase stuff. So do we want to increase 4? No, it's not necessary to increase 4. So the cheapest way is to just increase this 1 to 3 and also increase this 2 to 3. So in after doing that, and then this whole subarray will be valid. So let's change it back to the original value. So what I'm trying to say is that when you see a value that violates the non-increasing rule, so you need to keep popping stuff until it fulfills the non-increasing. So basically, you just find all the element that is smaller. In this case, it's just 2 and 1, and then we pop them out, and then we push 3 here because we pop 2 out. Now we have to somehow mark it. So the way that I'm gonna do it is to keep track of, instead of just the value, I'm going to have the frequency as well, because originally there's like 2 elements at front, which is 1 and 2. I kind of changed it to 3. So this 3 is the value and the 3 is the frequency. So the similar thing will be done here. So it's 4. There's like 4 and then 2. 4 is the value, while 2 is the frequency. Okay. So now it's pretty easy to know how much cost we have spent in order to make 3, which is like cost is, because we have to change 1 to 3 previously, so they're like 2, because 3 minus 1 is 2, and you also need to change 2 to 3. So 3 minus 2 is 1, so the total cost that we have used is 3. Okay, so now let's get back to here. So 3 is still okay. So it still doesn't violate anything, and the cost that we have used is 3. So let's take a look at the last element. We are trying to include this 6 again. So when we're trying to include this number 6 into the queue, so you notice everything here is kind of smaller than it. So that the way that we have to do it is to have the 6 and 1 at the beginning. 6 is the value and the frequency is 1, which indicates there's only 1 in here. So we have to pop these 3 first. There are like 3 elements here, and all of them are 3. So we have, as mentioned, we have this basically is this 3. So because of the previous operation, it has become 6, 3, 3. But that's not good enough. We have to change them to 6, 6, 6 in order to make them valid. Okay. So let me change back to its original value first. Okay. So this 3, 3, they're like 3, 3, 3. I have to change all of them to 6. So this frequent, I just need to plus them to, now that we have like 6, we have like 4 6. And then we can calculate the cost that we need to perform in order to make this this valid. So the way that we are going to calculate is pretty easy as well. So because they are all free, so each one of them we're gonna spend like 6 minus 3, and there are like 3 of them. So 6 minus 3 is 3, and 3 times 3 is 9. So now the cost is 12. As you can see, it's already exceeds what we can handle, but we don't care about that first. We're just going to, at least we want to make the queue valid first, and then we have to calculate like what do we need to do after. So now this 4 2, you can see is still not good enough because 6 is still larger than 4. So to put that on perspective is that you can change all of this to 6 and with like cost equals to 12, but that's still not good enough. You can, because you can see this 6666 and 44 is still not non-decreasing because this 2 4 is too small. We have to change this 2 4 to 6 6 as well. So again, let me just switch it back to the original value, and that's what we're gonna do. So we need to plus again 6 minus 4 is the cost that we have to do per item, and we have 2 items. So 6 minus 4 is 2, 2 times 2 is 4. So in total, they are like 12 plus 4, which is 16. And then the frequency will be added to 6, and here the queue now is finally non-decreasing. Namely, every element will be 6th by using the cost of 6th. But wait a minute, we only are allowed to perform 7 operations. That's why we have to pop something. You know, prior to that, we do not have to pop anything. So the first thing you're gonna pop is obviously R is n minus 1. So basically, if we're gonna pop, so we are looking at this element here, and we want to know what is the R that it can match. So obviously it cannot match here because the cost is too high. So we're gonna pop this, and then we can see like from the front, because it's actually going to be a deck where we're going to push everything to the front. And while we are doing that, when there are some invalid properties, for example, it is not non-decreasing, and it will popping from the right. So that's why when we're going to string the arrow, we're going to look for the front of the queue. So let's take a look at the front of the queue. You can see that the front of the queue is 6, and the original value is 4. So we know that it went from 4 to 6. So 0, 1, 2, 3, 4, 5. So R is originally 5. So we're gonna pop this R because it doesn't work. The cost is too high, and then we're gonna pop this and decrease the frequency, and this one will become 5. And because, as we mentioned, it went from 4 to 6. That's why it that's why we when we port it back, we can like spend 2 less. And similarly, 3 is still too hard. The cost is still too hard, and this will decrease by 2 again, and then we go from 0, 1, 2, 3. This one, and you can see like 12 is still larger, so we have to pop R again. So it's here. So basically I'm saying this 6312 is still not valid. So because this 2 originally is 2 and now is 6, because we are looking at the front of the queue, the first one is going to be 2. I mean the index 2, and the value is 6, as we can see right now. So we know that it went from 2 to 6. And that's why when we port it back, because it went from 2 to 6, it means that we can retrieve 8. We retrieve 4 back, which get the cost back to 8. But still, with cost equals to 8, it is still larger than what we are allowed to do. So that's why this 631 is still not good enough. And finally, we just need to go to 1, this 63. So basically it's this. So because again previously it was 1 and it went all the way to 6, that's why we can retrieve like 5 cost back. So now this 63 is valid again, so we can answer plus equals to the length of the current and valid subarray. So that's how we are going to calculate the total of the answer. So that's basically the gist of it, and let's see how can we actually turn this into code. Walk through the code. First, we are going to create the DAG, which we have mentioned before, and inside the DAG there's going to be a pair of integer. So the first one is going to be the value, and the second one is going to be the frequency. Let's call it dq, and we're gonna initialize like the size of the array. And as I have already mentioned, we need to keep track of an index called owl, so which just to indicate which one to pop if we're going to like pop one that is invalid. So we also need to keep track of the total answer that we need to return. Let's initialize it as 0. And the cost we are using so far, which to be safe, I just make it as long as well. Now that we have initialized enough things, let's just try to loop from right to end. So we are going to loop for the left pointer. Let's start with n-1 and all the way to 0 and l minus. So as mentioned, and I'm going to repeat again, is to check how many indexes that can match with cell. It is our target, and keep popping, or just do r minus equal 1 until numst l dot r is valid. That's basically the goal that we're trying to achieve while in this loop. Okay. So by the end of here, we are going to push something to the DAG. And if you still remember, the first value of the DAG is going to be the value, and the second value of the pair inside the DAG is going to be the frequency. So initialize, well, I'm going to initialize the frequency as 1, and then dq is going to push back numst l, which is going to be the value, and the frequency. So the frequency might not be 1, because when we're trying to pop something from the right, we will make the thing that it popped to nums L as well. So that's why the frequency will increase. As we already mentioned in the solution overview. So while stack is not empty, and stack dot back dot first. Remember, the first value is the actual number, the value. If it is less than or equals to nums L, it means that it is not going what we want. It is so because this is going out of order basically. So nums L is actually larger or equal to the previous one, the one that is on the deck. So we need to do something in order to make it in order. The way that we're going to do it is to just pair. We're going to pop the pair first. DQ dot back, and then DQ dot pop back. We're going to take the back and then pop it. Because this is invalid, then all frequency will need to be changed. So that's why the frequency will need to plus equals to dq dot back dot second, and the cost will be because we need to change everything to nums L, so it will be p dot first. That's how much we're gonna spend per item, and there are p dot second item there. Just to be safe, this one could potentially be very large, like this could be 10 to the power of 9, and the frequency here, p dot second, can potentially be 10 to the power of 5, I remember. So while this nums L minus p dot first will not overflow, when we times this p dot second, it's possible that it become overflow. So here we'll just turn it to long here, just to be safe. And once that's done, we need to push back nums L and the actual frequent that we're gonna do. Potentially we will have a lot of frequent here. And then so once we have done that, notice I haven't considered anything about K in here. We just need to spend, well, I didn't put any limit on the spending about the cost, so we just take whatever it has to take in order to make num L to num R that is non-decreasing. But just the next step is to make sure nums L R cost is within K. So if actually while the cost is too large, we need to keep popping out. That's what we're gonna do. So what we're gonna do, because we are pushing stuff to the queue in this way, so the leftmost of this stack is going to be the first one that you're going to pop, which will also happen to be arrow because we're going from right to left. So let's see, that's the one that we're going to pop. It's going to p dot deck dot front, and we're going to pop it first, pop front, and we need to we need to know how much we spend on this particular index. So the value right now is going to be to p-dog first. So we know that we might change it to be larger. So we need to minus back its original value. It is going to be allo, because the first one is going to pop is always going to be al. But once it is a pop, we need to minus the index, or minus. And then the frequent has to be minus as well. And then we know if there is more than one frequent, then we need to push front p, because we still have more frequent for this element. That's basically it. And once we're done, and we just return answer. That's pretty much it. Let's see if it works. There are two things. The first thing is that I forgot to add back the answer. So L minus L plus 1, as we mentioned, like the whole length, when it is valid and the cost is within K, the whole length, well, obviously you can start at L and you can end at L. I mean, we are always starting at L at this point. And we can start at L plus 1, and we can start with L plus 2 all the way to R. So that's exactly our minus L plus 1 choice that we can make. Okay, so because it's already popped back, so we cannot use dq.back. We need to use p.dog second here. Okay. Yeah, the span I need to spend here. Okay. Let's try to submit that now. Okay, and it is accepted. So the time complexity for that would be O. Let me see, did I sort somewhere? No, I don't think so. It is ON. Well, we do some sort of while loop in here, but you know, because we are using a DAC, so we don't actually like do a nested loop. It's more like n plus n. So because you know n plus n is just n in terms of ON complexity. So that's why we can just simplify it as ON, and for space it is ON as well, because we need to maintain this stack. And yeah, that's pretty much it. And thank you so much for watching, and I'll see you in the next video.